Hi everybody, I wanted to make this quick video to go over the examples for Couette and Poiseuille flow again because they're critical problems, and I wanted to make sure that you had some examples of these outside of class as well as the work we did in class. But I'll go relatively quickly here. So the first example I'm going to do is solving the Navier-Stokes equation for Couette flow. And remember the assumptions here for Couette flow. So first off, I guess I'll outline the geometry. So we have two parallel plates. The upper plate is moving at a velocity u. The lower plate is fixed. It's just sitting there. And I'm going to make the following assumptions. I'm not really justifying these assumptions to you. They're assumptions. They're what give me Couette flow. If I change these assumptions, I get a different flow. So I'm assuming the flow is steady. That means, if you recall, that the time derivatives are 0. So the time derivatives of the velocities are 0. I'm assuming the flow is 2D, which means that my derivatives in the z direction are 0 here. I assume that the flow is unidirectional. So that means I'm going to assume that the velocity is only in the x component direction. So let me actually get rid of that. So I only have the x direction. And what we'll see is that it only makes sense that it changes in y. All right, because what this is going to imply when I say it's unidirectional, that implies that Vy equals 0 and Vz equals 0. But through the continuity equation, that also implies that the derivative of x in the x direction is 0. And that one comes from the continuity equation. We talked about that in class as well. You can verify that on your own. If you write out the continuity equation and you assume that Vy and Vz are 0, you get this. And then we're going to neglect gravitation, and we're going to assume that there's no pressure difference on the two different sides of the plate, in the front and then the rear of the plate. So let me write down the Navier-Stokes equation in the x component. So I have rho dvx dt plus vx dvx dx plus vy dv, this is always one I forget, dvx dy plus vz dvx dz equals, and that's so long I'm going to come down here on this next line, minus dp dx plus mu, and I have the second derivative of vx with respect to x squared plus the second derivative of vx with respect to y plus the second derivative of vx with respect to z. I forgot to put the little 2 there, plus rho g in the x direction. Okay, so the first step in the problem is to write down the geometry, to get the assumptions, and to write down my governing equations. That's steps 1, part A, B, C. So the second step now is to use these assumptions to cancel out the relevant terms. So I said the flow is steady, so that means that one is gone. So that's because it's steady. Then I said the flow is two-dimensional, so that means anything with a ddz or can go away, or with the vz. So that one goes away because vz is 0, and here I don't care about the z derivative there either, so all my z's are gone. That's from two-dimensional. Now unidirectional, so I say that vy and vz are 0, so this vy is 0. I already took care of the vz's. And also any derivative of the x component with respect to x is 0. So that's that one, dvx dx squared and dvx dx. So that one's gone. All right? The last two are, I say gravity is not important, and certainly in this case there's not going to be anything in the x component, so that one's 0. Recall that the g vector, which is gx, gy, gz, is equal to 0, 0 minus g. Okay, so gx is 0, so that's gone. But the fact that I neglect gravity also means that I can neglect it for the pressure in the y component. So I don't have to solve for that one. And the last one is to say there's no pressure difference between the front and back part here, and that means I can cancel that guy out. So I'm left with 0 equals mu the second times the second derivative of x with respect to y. And I can divide by mu there, and that's going to go away. So now I'm left with the math problem of this differential equation here, but I also need the boundary conditions. So I need to know what Vx is on my boundaries, both at 0 and at h. So Vx at 0, I said this wasn't moving, and so by the no-slip condition, I know that the velocity right above here has to equal the velocity of that plate, so I know that that one is 0. And by the no-slip condition on the top, I know that the Vx at h has to be equal to the same as the velocity of the plate, so that is u. So now I'm left with the math problem, this boundary value problem at second order ODE. So this now becomes an ODE, so I can write this as a total derivative. dy squared equals 0. And this is just integrable. So the first step to integrating it, I can say that this is a derivative of dvx dy equals, and over here I have 0 dy, and I can integrate both sides. And when I do that, I end up with a solution here. Excuse me, not my solution yet. Put that back in. Well, that was a terrible one. That back in. I end up with dvx dy is equal to, now the integral of 0 dy is just some constant. I'll call that c1. Now I integrate again. Integrating again gives me the derivative of vx on one side, and on the other side I have the integral of c1 dy. So that now gives me vx on this side equals, and this will now become c1y plus c2. And now I need to resolve these constants, which I use my boundary conditions to do that. So I can evaluate these. Vx at 0, I plug in 0 for y, so I get c1 times 0 plus c2, and that is going to equal 0. And what I find there, since that goes away, is that c2 equals 0. And then I take Vx at h, and I put now c1 times h, and what does Vx at h equal? It equals u. So now I can solve for c1, which is u over h, and giving myself a little more space down here, I can say that Vx as a function of y is going to equal c1y, which is u over h times y, plus c2, which I said was 0. So I've solved it. Alright, so that is Couette flow. So now we're ready to move on to our second example. Let me get a new page here. Let me come up here, page. Alright, and we can do B, Poiseuille flow. Okay, so now in Poiseuille flow, I'm going to have cylindrical coordinates now to look at a pipe. Alright, and so my coordinate system looks like this. R is in the radial direction, and Z is in that direction, the down the pipe direction, and then I have theta that's going around, it looks like clockwise sort of. I'm going to call this distance R, and I will call here Z equals 0, and over here I'll call that Z equals L. And I'm going to assume that at Z0 I have a P, a pressure at 0, and a pressure at L. And remember from pipe flow, we would expect that the pressure at 0 would be greater than the pressure at L. So we're pushing the fluid in this direction. All right, so my assumptions, so I'll put over here assume. I'm going to assume that the flow is steady. I'll assume that the flow is axisymmetric. Okay, remember what axisymmetric means. Axisymmetric means it's symmetric in the in this direction around theta. And the last thing I'll assume is that the flow is unidirectional. And what I mean there is that I assume I have Vz, all right? That's my only velocity component. I don't have a Vr or a V theta. So Vr equals 0, V theta equals 0. All right? And we can go through the continuity equation, and we'll also find that that means that, by continuity equation, we find that dVz dz also equals 0. Okay, and you can show that's true, assuming those two things. So the unidirectional flow plus continuity equation implies this. Axisymmetric, that means I'm not going to have any changes in the theta direction, and steady is again my time. dVz dt equals 0. All right, so we can take our cylindrical coordinates, our Navier-Stokes equation and cylindrical coordinates now, and write it down. So I have rho dVz, oops, that Vz is kind of terrible. Let me rewrite that. dVz dt plus, now I have this, all just comes from, you can look this up in the table in your book. I'm copying it down from my notes here. Vr dVz dr plus V theta over r dVz d theta plus Vz dVz dz equals minus dP dz plus mu times 1 over r, the r derivative, ooh, that delta, let me fix that one because it's kind of ugly, dr of r dVz dr plus 1 over r squared dVz d theta. Those have squares on them, as they should. And I'm running out of space down here, but I have a second derivative of Vz with respect to z, close brace, minus rho gz. All right, so that's the Navier-Stokes equation. So now I need to take my assumptions and cancel out terms. So let's review. So steady, that's the time term. So I take that one. That one's 0. The next is I say the flow is axisymmetric. So that means anything with respect to theta is gone. That one is gone. And that one is gone. That's kind of like the 2D assumption, right? It's still a three-dimensional flow, but it eliminates one of my directions. The next one is to say the flow is unidirectional. So that means Vr is equal to 0. So no Vrs, no more Vrs. V theta is equal to 0. I already said that guy was 0 because of V theta. So that one's gone, fine. And then by continuity, because of unidirectional flow, dVz dz is gone. So that one is gone, and that one is gone. Okay? But I have left 0 equals, let me see here, minus dP dz plus mu times 1 over r d dr r dVz dr, close brace, minus rho gz. Now I'm going to assume for a minute that I don't know what direction gravity is in. As I've drawn it, it makes sense to have gravity in that direction. but I could have drawn a tilted pipe, and maybe that would mean gravity's in that direction, or gravity's in that direction. Okay? I don't know what direction gravity's in. So in that case, I'm not going to neglect gravity, and as I told you before, I'm going to, as I said in class, I'm going to take my pressure and I'm going to define a dynamic pressure, which is equal to pressure plus rho gz, so that if I write d dynamic pressure, I get dp plus rho g. And that's very useful because I have right here derivatives of pressure, so I can rewrite this now as 0 equals minus d dynamic pressure dz plus mu times these other guys, 1 over r d dr r dvz dr. Okay? And that pressure is maybe not the best P ever. And I'll try and be careful to make sure I say when this is a dynamic pressure or not, but you've hopefully had enough experience with the dynamic pressure that this isn't too confusing for you. If it is, please ask me and we can talk about it a little more. Okay, so now we're to the point where we need to do some math. So we have this guy here, this is our equation, and we need boundary conditions. So the first boundary condition that we can say is we look up here and we say, well, by no slip, I can say that the velocity on the edge of the pipe is 0. All right, so we can say that. So Vz at big R equals 0. So that's no slip. But I have a problem in that I can't say no slip anywhere else. But I can say that the velocity has to be bounded. Okay, and we'll see where that comes in a minute. So in other words, I'm saying that the velocity can't be infinity. It has to be something less than infinity. And we'll find out that that works and is useful enough as a boundary condition. Okay? So, all right, so now what do? So I have to solve this guy. Well, I told you that we were only going to end up with ODEs, but we have this thing that has derivatives of r and this that has a derivative of z. But if you notice here, I can take my pressure and put it on the left-hand side, and I can take this guy and leave it on the right-hand side. Oops, I want to do my ddr, ddr, r dvz dr. So now, if I look at this for a minute, this is telling me I have some function over here, okay, and pressure changes as a function of z. But pressure doesn't change as a function of r. It only changes as a function of z. So the dynamic pressure is a function of z only. So that means that the derivative with respect to r is equal to 0. And this guy over here, I told you that Vz is a function of r, not a function of z. So that means that dvz dz equals 0. Well, if that's true, if I took the r derivative of this side and I took the r derivative of this side, I'd still get a function over here, but that would equal 0. Okay? Or if I took the z derivative of both sides, then I'd get something over here, but this would equal 0. So what that tells me is that if I integrate back to this point, that these two have to equal a constant. So dp dz has to equal a constant, which also has to equal mu 1 over r d dr r dvz dr. Okay? So what this says is that if I have two functions and they covary with different variables, they have to equal a constant. So if I've got something, maybe you can kind of think about it like this. I have some space, right? This is a little funky, but let's say x and y. And something goes like this and something goes like this, and they're varying and they're equal. The only place they can be equal is at a number, right? I'm trying to give you a little intuition for this. If this still doesn't make sense, you can come talk to me. Okay? All right. Oh, so now I need a new page. Okay. So now that I know that this is a constant, I can solve for the pressure one first. I can solve either of them first, but the pressure one's particularly easy. So I say dp dz, and I'm writing these as total derivatives because I know that p is only a function of z, is equal to c. So I just integrate that. So now I say that p is equal to c times z. Well, this is a constant, and I can figure that out just fine from what I said before. I said that p at 0 was equal to p0, and p at L was equal to PL. So I plugged those in here, and so P at 0, I said that's going to equal C times 0. So that just tells me that's 0. I missed something. Didn't I? Oh, I totally missed something. Let me back up here. When I did this integral, I totally forgot to add another constant. That's why I was getting confused here. So when I take this integral, I have c times z. I forgot to add some other constant. I'll call that other constant b. So now when I put in p0, I get c times 0 plus b. So I get that b has to equal p0. That makes lots of sense. So b equals p0. And then I can do p at L has to equal c times L plus p0, which is b, and I get that c equals pl minus p0 divided by L. Oh, well, that makes lots of sense, right? Look, this is just the rise over the run, right? This is the change in p over the change in L. And I said dp dz was a constant. Okay, so that's great. So c equals delta p over L. All right, and I've kind of been writing p's. I should be writing dynamic p's, but it hurts my hand, so I'm just going to, I'll fix it as I go down, but sorry about that. Okay, so I found c, and now I'm ready to solve this guy over here. Okay, so now I'm going to say 1 over r d dr of r dvz dr is equal to c over mu. So I just divided the mu over so I didn't have to put brackets, which I said was delta dynamic p over mu L. All right? So now what do I do here? Well, I'm going to separate and integrate. So I can do that. I'm going to put on this side, I have the derivative of r. I'm going to write those as total derivatives. So I'm going to make the partial derivatives go to total derivatives because Vz is a function of r only. Okay, so I'll just rewrite that. So now I have the total derivative of r dvz dr is equal to, and I multiplied by r, so I have delta dynamic p over mu L r, and then dr, and I integrate both sides. Okay, so this side, just I'm taking the derivative of that stuff in there, so this becomes r dvz dr, and on this side I get an r squared over 2. So I get delta p over mu L r squared divided by 2 plus constant. And I'll just call that C1 for now. So now I need to keep going with math. Divide both sides by r. So I get dvz dr is equal to delta dynamic p over mu L r over 2 plus C1 over r. And I can integrate again. So I'm going to put dvz on the one side. And I have delta dynamic p, put a little curl there, mu L r over 2 plus C1 over r. Put all those in parentheses. We'll put it dr, and we'll integrate both sides. All right, so this side will now give me Vz, and this side I'm going to get r squared over 4 delta P over mu L R squared over 4 plus, all right, this C1 over R, what's the integral of 1 over R? That's a log. C1 natural log R plus C2. Okay, great. So now let me think about applying my boundary conditions. I told you that VZ at big R was equal to 0, and I said the other one I'm going to need is that VZ has to be bounded. All right. So let's apply this guy, this one, the bounded condition first. What happens when R equals 0? If R equals 0, this guy's fine. That one goes to 0. That guy doesn't care, it's a constant. But that guy, it blows up. C1 log R approaches infinity. All right? And R, of course, can be 0. That's the center of my pipe. Right along there, center of my pipe. Well, the center of my pipe, I can't have velocities that are infinite along the center of my pipe. So, in order for my velocity to be bounded, C1 must equal 0. Okay? So that tells me what C1 is. C1 is equal to 0. So now I can apply the other condition. I say that VZ at big R has to equal 0. I do that by applying this to the equation. Delta P over mu L, big R squared over 4. I said C1 is 0, plus C2. Well, that makes solving for C2 pretty easy. C2 is just the negative of that. So C2 is equal to minus delta dynamic P over mu L, big R squared over 4. Okay, so now I have my final solution. I can say that VZ as a function of R is going to equal delta dynamic P over mu L, and then I have R squared over 4 minus big R squared over 4. I can simplify that a little bit. I can pull out the 4, and I can pull out an R squared if I want, and I can get delta P over 4 mu L, and then I'll put an R squared here, and I get R squared over big R squared minus 1. Okay? And a lot of times this is written the other direction, because remember that delta dynamic P is usually less than 0, because dynamic P L is often less than dynamic P 0. So because of that, people often flip this sign around and pull the negative sign out. So they write VZ as a function of R is equal to minus delta dynamic P divided by 4 mu L with an R squared out front, 1 minus R squared over big R squared. Okay, and that, if I have the hands to do it, sorry for the handwriting, is Poiseuille flow. Okay, I want to do, let me just point out, remember, this is parabolic. Look at that. So if this is my pipe, this tells me that in the center, I've got, if I put in 0 here, I get that guy, so I'm big there. So if I draw my thing off, I'm big there. And I should, when I go to big R, I should go to 0. So I'm 0 on the ends, and I'm a parabola in shape because of my squared profile. Okay, it's probably the worst parabola you've ever seen drawn, but it's the best I can do with the current medium I've got. Okay, so I have a parabolic flow profile, we say. I'm going to do one more quick thing, maybe take 5 more minutes here, and show you how to get the friction factor for laminar flow. So I'm going to come up here, page, new page after. Okay, so let me put this, I'll do C and I'll say friction factor. Okay, so how do I get the friction factor? Well, remember, the friction factor I said was the wall shear stress divided by 1/2 rho u squared. So there's 2 things that I need. I need this guy and I need that guy. So I need tau w, which is the wall shear stress. Okay, and I need the average velocity. Okay, so how do I get that? So let's see, let's get the average velocity. Okay, how do I get the average velocity? Well, if I tell you, hopefully this will make sense, the flow rate is going to equal the integral of the velocity in my z direction over the area, right? Integrating over the area. So I have this area here, and I've got my VZs all along that direction. I want to integrate over that whole area. That'll give me my flow rate. This is kind of like saying U times A, right? But now I want to get all of the different velocities. Okay? So now if I want this, I said this is true. Q equals UA. So if I divide both sides by A, I get U. So that will be U is 1 over A integral of VZ dA. The other way to think about that, so one way to think about it is getting it from the flow rate and then dividing by the area. The other way to think about this is a definition of an average. So if I sum something up, and then I divide by the number of those things, xi. Okay, that's an average. That's the same thing that's going on here. I'm adding up all of these and dividing by that. So I'm just calculating the average velocity. So let's calculate the average velocity. So, excuse me. Alright, U is equal 1 over, what's the area? It's pi r squared. And my integral here is going to be from 0 to 2 pi and 0 to big R, Vz as a function of R, d, let's see, I put in theta, I forgot the R, don't forget the R d theta dr. Okay, so this is just math from here on out, but let's do it out because we have a little time because we're in an example video. So I can do the d theta integral first. That'll just give me a 2 pi. So I get 2 pi divided by pi r squared. Now I have the integral 0 to r of Vz of r dr. Pi's are going to cancel. And Vz was, I just wrote it up here, right there. It's that guy. I'm going to call all of this for a second. I'm just going to call that a constant to make my life a little easier while I do the integral. So I'm going to call this 2 divided by r squared. I have the integral from 0 to r. And I'm going to call this k times 1 minus r squared over r squared, where k equals minus delta dynamic p over mu L r squared divided by 4. Okay, which is what my other piece was up there. Okay, so now I'm going to do the integral here. This integral gives me, I can pull that constant out, and I can integrate, this is r dr. So I have an integral of r, so let me write this. I pull 2 over r squared, and I guess, I don't know, defining the constant, that was kind of a dumb idea, so sorry about that. I'm just going to write it here. Delta dynamic p divided by mu L r squared over 4. Look at some of that stuff's going to cancel. And now I have the integral of 0 to r. Let me multiply this through. R minus, and then I'll put r cubed divided by r squared dr. Okay, r squareds cancel. The 2 cancels with that 4, and I get a 2 down there. And I get a minus delta p, dynamic p, over 2 mu L. And then let's see, even I can do polynomial integrals. That will give me r squared over 2 minus, this will be r to the 4th over 4 big R squared. And I'm going to do that from r to 0. The zeros are going to be easy. That'll just be 0. So I'm going to end up with minus dynamic delta p divided by 2 mu L. And I'll have big R squared over 2 minus big R to the 4th divided by 4 big R squared. Well, the R squared cancels with that to give me an R squared. And I get R squared over 2 minus R squared over 4. That gives me R squared over 4. So this is minus dynamic delta P over 2 mu L times big R squared divided by 4. Whew, it's kind of a lot of algebra. I end up with really ugly U. U is equal to minus dynamic delta P divided by 8 mu L, and I have an R squared. So now if you go back and compare this to our solution for VZ, look, up here I have minus dynamic delta P over 4 mu L R squared. That is just 2 times U. So I can rewrite VZ as equal to 2U times 1 minus R squared over big R squared. That'll make my life a lot easier. Now I don't have to carry around those delta P's and the 8 mu L, all that stuff all over the place. Okay? That's another reason why people write it like that. So this is my average velocity. Don't get tricked by the minus sign here. Remember that delta P is negative. Okay? So that's a positive number. Alright, so the last thing now, new page after, okay, is to calculate the friction factor. So that, or to calculate, the wall shear stress. So we need to get tau W. Okay, well what's tau W? Tau W is going to be tau, the wall shear, the viscous stress tensor evaluated at the wall, which is at R equals big R. Okay? But in this case, we don't need the whole guy. We only need tau RZ evaluated at R equals big R. So why is that? So if I've got my pipe, okay, up here, what is this? I'm looking for the shear stress at the wall. So the normal direction, okay, is in the R direction. So that's that one. And I want the Z component, only the part down. All the other parts are going to be 0. Okay, so I only want tau RZ. So if I go look up tau, if I go look this up in my book, I find that tau R, there's, different components, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, I only want the RZ component. So I look up what tau RZ is, and tau RZ is equal to mu times dVz dr plus dVr dz. Okay, well, dVr dz, that one's 0. Remember, I have no velocity in the R direction. So I only need to evaluate this guy, dVz dr, and to get the wall shear stress, I need to evaluate that derivative at R equals big R. Okay, so now let's evaluate that derivative then. So tau wall is mu, and dVz, I'm going to take the R derivative of what Vz is. Well, I just wrote it right there. It's 2U times 1 minus R squared divided by big R squared. Close my big parentheses. And I need to evaluate that after I take the derivative at R equals R. Okay, so let's do that. I'm going to get mu, R derivative of this guy, so I can pull 2U out. R derivative of that is 0. I'm going to get a minus sign, 2R divided by big R squared. Evaluated at R equals big R. So that's 2 mu U multiplied by negative 2 big R divided by R squared. Squared cancels there. And I get that the tau wall is equal to minus 4 mu U over R. Hey, that's looking pretty good. I have that the wall shear stress is proportional to mu U over R, which looks a lot like mu U over D, which is what I had before. And really, I don't care about the negative sign. That tells me what this is, but I only care about the absolute value of tau RZ. So I'm going to say that my wall shear stress is my absolute value of tau RZ evaluated R equals R. And that's going to give me 4 mu u over R. Okay? And that's just for my version in the friction factor. I don't care about the negative sign. So now to calculate the friction factor, I say the friction factor is equal to tau W over 1/2 rho u squared. Well, I ended up finding tau W in terms of u, so I can just plug that in. So I have 4 mu u divided by R, and then I have 2 rho u squared. So the 2, that gives me an 8 on top. Mu u, I have a u that cancels here, and so I get a mu over rho u r. This is a u there, and that's a mu up there. Okay, r, well, I want to write that in terms of d. So that's going to be 16 over mu over rho u d, right? Because r equals d over 2. So if I plug that in, d over 2, well, look at that. Rho u d mu, that's 1 over the Reynolds number. So the friction factor is 16 over the Reynolds number. And that is the friction factor that we had earlier in class for laminar flow. Okay? All right. That's all I got for you.